Want to hydrate on the moon? I'm not sure. Is there enough water? Let's find out. In this video, I'm going to share with you 4 things. 1, the phenomenon that got my students excited to learn more about hydrates. 2, GIF animations and videos that show you how my students determined the amount of water in copper sulfate. 3, handouts for you to use in your chemistry classroom, right in the link below, with the key. 4, the actual standard, the Next Gen Science standard that this is linked to. Let's start with number 1, the phenomenon, the anchor phenomenon. There is water on the moon. It's not very much, 100 to 412 parts per million. That's a very small amount in terms of concentration. Let's put that into layman terms. We can equate that with a 12-ounce water bottle present in about a cubic meter, remember a meter is 3 feet, of soil. Where was this water found? Well, on the moon in the Clavius crater that you can see right here in this animation. So that animation came from NASA's Scientific Visualization Studio, and the findings were published in Nature, titled "The Molecular Water Detected on the Sunlit Moon" by Sophia. Who's Sophia? Sophia is NASA, our National Aeronautics and Space Administration, and DLR, Deutsches Zentrum für Luft- und Raumfahrt, Stratospheric Observatory for Infrared Astronomy. That's a mouthful. The word that stuck with me was stratospheric. So that spacecraft must have gone up into the stratosphere, as you can see right here. Obviously, they were observing the moon, not the sun, as shown in this picture. How high is the stratosphere? Well, this graph shows it's roughly 12 to 48 kilometers in altitude. So that's the phenomenon. There's very little water present on our moon, but not inside a lake or a stream or a river or an ocean. It's present inside rock. So rock can have water in it. How can we determine the percent composition of a hydrate? And the rock that we're going to choose is copper sulfate. The accepted value is copper sulfate penta, that would be 5, hydrate. 5 molecules of water surrounding the copper sulfate. I gave my students 2 methods to do this. The first method that you see here first requires grinding up crystals of copper sulfate hydrate and then heating it up using a butane burner after the crystals have been turned into powder. Upon addition of the heat, the water goes away and it turns the hydrate into an anhydrate. So again, the evaporating dish method, we start off with hydrate crystals, we grind them up using a mortar and pestle, and then after some heat has been applied, we get out of it anhydrate. Hopefully not so much clumps, maybe better to have fine grayish powder, but you get the idea. The other method is a test tube method. Let's check it out. So don't do that. All right, so we're going to heat up the test tube with the finely ground up blue hydrate powder, copper sulfate, and over time, that blue powder is going to turn into a grayish powder. Obviously, you see some problems here, right? So this alternate method, we start off again with the hydrate powder. And after a while, after enough heat has been applied, we get anhydrate clumps, but you already see a little issue there because in the neck of that test tube, a little bit higher up, you see a lot of H2O condensation. What might that do to our measurements? What might that do to the mass that we're going to take after the heating has been completed? For this lab, you can use Flinn Scientific copper sulfate, either crystals or powder. I actually didn't have the powder in my stockroom. I only had the crystals. And actually, I kind of liked it. It gave my students that extra step to take that rock, to take those crystals and grind it up and therefore I felt they were more involved in the process of trying to get that water out. First step is to increase that surface area of the crystals by turning it into powder. If you don't just want this handout for the Hydrate lab, but you want all the resources that I've created YouTube videos on, there's a second link in the description below that leads you to my landing page. It's got everything. And again, at no cost to you. You are welcome. All right, we've got the phenomenon. There's water on the moon. How can we get water out of rock if there is no water present? 2, I shared with you the 2 methods that I tried with my students, the evaporating dish method and the test tube methods. Let's now look at the handouts. We have our title, How to Determine the Percent Composition of a Hydrate. We've got our 2 different setups, the evaporating dish and the test tube setup. We've got our hydrate, and we're also seeing what the anhydrate should look like. Students are simply going to come up with the purpose of the lab. What is the percent composition of the hydrate? They are to write out what their materials and procedures are, or materials and methods. And the key thing is, I do give them a data table in advance because this is complicated enough that I'm not letting them construct a data table on their own. I help them with one of the 2 sets of data. So either the test tube that they're doing or the evaporating dish. And then the next lab cell, they switch, and now I do not help them how to figure out the actual data gathering and data analysis because I've already done it once with them. They have to make sure that they show their percent error work based on the copper sulfate pentahydrate accepted value. And they have to show also how they figure out the empirical formula based on the mass of the hydrate and the mass of the anhydrate that they measured. As always, a key is handy to have. I'm showing you here some sample data that I've obtained with my students, sample test tube data, and sample evaporating dish data. And what you should notice is that the test tube data shows you an underestimate in terms of the water percentage, whereas the evaporating dish data tends to show an overestimate of the water composition. I've included here the percent error work and the empirical formula work, and then the crux of the lab is, of course, to complete that data table and come up with a conclusion. So their conclusion is based on their personal or lab group data, but then I also compile all the data from every lab group in the class, both the test tube and the evaporating dish. And then we're going to see what is the overall trend. So I hinted earlier that with the test tube, we tended to get an underestimate. With the evaporating dish, we tended to get an overestimate. And I will confess, I checked OpenAI, ChatGPT, to get some help what might be good possible reasons for the overestimate with the evaporating dish and the underestimate with the test tube. And it was very interesting to see that my students actually came up with some good suggestions that were similar to what ChatGPT suggested. The test tube, as we saw in a picture earlier, clearly showed condensation higher up in the tube. That's an error that may lead to an underestimation. The evaporating dish tends to work better because there's way more surface area. And in general, we got better data with that. But it's good for students to figure that out. Why are we doing certain things a certain way in the science laboratory? What standards is this lab connected to? It is specifically HSPS1-2, abbreviated as simple chemical reactions. Again, these standards are 3-dimensional, so students are involved in constructing explanations and designing solutions. They are learning about the structure and properties of matter, chemical reactions, and the relationship between energy and forces. And they're going to notice a pattern. These are, again, the next-gen science standards, or for those of you in New York State, like I am, the the New York State Science Learning Standards. We have reached the conclusion of the video, Want to Hydrate on the Moon. Thank you very much for watching. Bedankt voor het kijken en tot ziens. See you in the next video.